All right, so we're going to talk about today chapter 1, starting off. And heat transfer. What is heat transfer? Heat transfer is the exchange of thermal energy due to a difference in temperature. So there has to be a difference in temperature in order for there to be heat transfer. There's a difference. You can heat a turkey in your oven, and look in there when the oven's on, and you'll see it glowing red on the coils. Or your toaster, look in there, you'll see electrical wires glowing red. Wires are hot. The toast is cool. The bread's cool. There's heat transfer occurring because there's a difference in temperature. Look in your microwave, turn it on. You say, the side walls are glowing red. Well, if they are, get out of the kitchen real fast. That's bad news. Nothing's glowing red, but there's heat, there's transfer of energy taking place. What kind of energy? Microwave energy. So there's thermal energy and there's microwave energy. We're talking in this class about thermal energy. That's a difference. Go back to thermal. You've had thermal, it's a prerequisite. This is the first law for a closed system. Equation, Q equal delta U plus W. In thermal, let's say it's a piston cylinder, you're taught how to find delta U. Give me some pressures and temperatures of air in the piston cylinder, and I'll tell you delta U. I can find it from the tables. W was called the work done during the process. In the chapter on work, they always give you a few equations on how to calculate work. The first question they ask you is the process constant pressure? Is it a polytropic process? Is there spring work being done? Is there electrical work being done? They give you equations for that. Now comes Q, heat transfer. Try and find one equation for Q in that thermal text. There isn't any. Here's what they'll say. The heat loss through the turbine, insulated turbine, is so many BTU per hour. They give you Q in thermo. Or they'll say, if this much work is done and the process goes through this temperature and pressure, how much heat transfer occurred? But they never tell you how to calculate heat transfer. That's why we have this class. This class is meant to fill in one of those blanks. How do we find that Q? Okay. So in heat transfer, we pretty much lump in the first course heat transfer into one of three modes, or three ways that heat can be transferred. Number one, it can be transferred by conduction. Number two, by a process called convection. And number three, by what we call radiation heat transfer. Chapter 1 briefly goes into these three modes of heat transfer. But then we get into depth in conduction in chapters 2, 3, 4, and 5. We get into depth in convection in chapters 6, 7, 8, and 9. And we cover radiation in chapters 12 and 13 in more depth. But chapter 1 is an introduction to those three modes of heat transfer. So we'll start with conduction. Conduction heat transfer, HT. Transfer of thermal energy from more energetic to less energetic particles due to their interaction. If I heat a steel plate on one side with some kind of a welding torch, or you can put a Bunsen burner under it, heat one side of that steel plate. The molecules in there start to vibrate They get more energy from that heat. They vibrate. They interact with their neighbors, exchanging energy. And the energy exchange goes from the hot side of the steel plate to the cold side of the steel plate. By what? By conduction. So that's what occurs in conduction. Now, we can then look at how we calculate conduction. And to do that, we'll write down Fourier's law, the governing law. Okay, this is the basic one-dimensional form of that law. First of all, what is Q? Okay, here's what Q is. Q is called the heat rate. Heat rate. It's in watts. You can call it the heat transfer, but it's officially the heat rate. It's in watts. What does the double prime mean? It means per unit area. Q per unit area means take Q, divide it by the area in square meters, and the units then become watts per square meter. Q with no prime is watts. Q double prime, watts per square meter. The heat transfer in this case is in the x direction, so it's a one-dimensional heat transfer case. It's officially in Chapter 2, three-dimensional, and we'll do that later on, but for right now in Chapter 1, it's one-dimensional. So the heat transfer is in one-dimensional x. So, for instance, if this inside the wall, make something up, is at 100 degrees Fahrenheit, and the hull side on the wall is 30 degrees Fahrenheit, there's going to be some heat transfer through this concrete wall from the inside here to the hull side here. Which direction is it in? Hot to cold. This way. That's my x direction. X direction this way. Heat transfer occurs what direction? X direction this way. So that's what this means. Now, that K is a property of the material, in that case concrete wall. K would be the K of that wall at what temperature? The average temperature, 100 plus 30 divided by 2. So K is a property called the thermal conductivity. It's in watts per meter K. Our textbook is all in SI, for better or worse. For you, it's for better, until you graduate, and then you say, oh my gosh, I got to convert these guys into whatever, English engineering or back to SI. So the good news is everything's in SI in this textbook. Homework, examples, etc., which makes life tons easier. Okay. Where do you find K? Back of the book. Give me a fluid, or give me a substance. Okay, aluminum. Give me a temperature, 500 degrees C. Go to the back of the book. There it is, right there. Material and temperature. Now, if we look at this, let's draw a wall here. And I'm going to measure this X in this direction, and the wall thickness is L. And I'm going to assume the temperature on the left-hand side is a hot temperature, T1. The temperature on the right-hand side is a cold temperature, T2. Material has thermal conductivity, K. This is one-dimensional heat conduction. We'll discuss that in chapter 2 and 3. But for one-dimensional heat transfer, we can get rid of the ordinary differential dt dx and replace it by T2 minus T1 divided by L minus 0. That's one-dimensional heat transfer. We can just put that up here, 1D heat transfer. Turns out, for that case, the temperature profile is linear. We'll discuss that also in, I think it's chapter 3. Chapter 3, linear. Now, let's replace the dt dx with this then. So we get q double prime x equal minus k T2 minus T1 divided by L K T1 minus T2 divided by L K delta T over L. So that in chapter 1, this is the important equation from Fourier's law for how we find conduction heat transfer through, for instance, a wall. Now, if you don't want the answer in double prime, let's say, no, I want Q in watts through the wall. Okay, well, what do you do to Q to get Q double prime? You multiply Q double prime by the area to get Q. So, Qx equal K A delta T over L. Area is the normal area. So if the pen is the heat flow direction, the appropriate area is the area of my hand. Here's the heat flow. Here's the area I put in. If it's this wall and the temperature of this side is 100 degrees C and the temperature out here is 30 degrees C, the correct, which way is the heat flow? From the hot inside to the cold outside. Heat flow goes that way. What area do I use? The height of the wall here times the length of the wall. Rectangular area, height times length. Okay, I think that's probably all we need. Oh yeah, one other thing. You say, well, oh, by the way, this law came from Professor Fourier way back, you know. But he didn't derive it from something. He did some experimental investigations. And he found out that this is the way the heat flow seemed to respond to a change in temperature or change in length or change in material. So he derived this thing from looking at experimental results. But you might say, boy, I don't understand him. Why would he put a minus sign in front of that? I mean, that sounds ridiculous to me. He put that there, really? Professor Fourier? Well, yes, you have to. He figured it out. You have to. Here's a picture. Hot temperature, cold temperature. You know which way heat flows, from hot to cold. Q. Which way does it flow? Positive, negative x. Positive x, positive x. What sign is that Q? Positive. What sign is dt dx? Look at it. Negative. What's K? It's always a positive number. It's a property. Does it check out? Oh, it sure does. Plus on the left, on the right, minus sign, plus sign, minus sign. Yeah, it checks out. If you don't do that, minus sign, it says, you know what? The heat flows in the negative x direction. Oh, no, it's not. Heat always goes hot to cold. That's why I put the minus sign there. Okay, so that pretty much wraps up Chapter 1, Conduction. Next week we'll cover chapters 2, 3, 4, and 5 in great depth on conduction. All right, so now we're going to change this to convection. All right, so let's get that down. If you go back to your background in fluid mechanics, by the way, in order for there to be convection, there's a fluid flowing over a surface, convection, a fluid flowing over a surface. That's fluid mechanics. So we go back to fluid mechanics. So here's our surface. If you recall from fluid mechanics, there was a boundary layer that would build up on a surface with the fluid flowing over it. And the boundary layer would look like this. This may be called U infinity, and this is be called U as a function of the vertical distance y. Okay, that's fluid mechanics. Well, how about heat transfer? Okay, let's say the surface is at a warm temperature, T sub s, and the fluid, maybe air, is at a temperature T infinity. So a boundary layer builds up for heat transfer called the thermal boundary layer. This is the surface temperature Ts. The free stream temperature T infinity, which is cooler. So now we have a boundary layer that looks like this. That's the temperature or thermal boundary layer. But you can't work the heat transfer problem unless you really understand what's going on from fluid mechanics. That's why fluid mechanics is a prerequisite to heat transfer. We have to really have a good feeling for fluid mechanics in order to tackle convection heat transfer. All right, so the rate equation is Newton's law of cooling. Q equal H A T S minus T infinity. Okay, we've defined Ts and we've defined T infinity. A is the surface area. That's the area touching the fluid. The surface area in contact with the fluid. I'm going to put here convection heat transfer, just so we know. Between surface and fluid. To have convection, we have a surface and we have a fluid. and the fluid is moving over the surface. Okay. Surface area A. Take that pen. The pen's hot. The air in this room is cooler. Convection heat transfer. I blow air over it. There's the equation. What's the right area? Pi d times L, there's L. That area, pi dl, okay? Pi d, circumference, L the length. Where does the air touch the fluid, or touch the surface? That's what it means. So that's our basic convection equation. Now H. H is the convection heat transfer coefficient. Depends on fluid properties. It depends on geometry. Depends on flow regime. And possibly others. First question is, what's the fluid? What's its temperature and pressure? From that you find the properties. Second question, what's the geometry? Is it a circular tube? Is it a flat plate? Is it a sphere? Second question. Third question, is it laminar flow, turbulent flow, mixed flow, cavitation? What's the flow regime? What's going on there? All those things are tied into H. You won't find H in the back of the book in the appendix because it's way too complicated, way too complicated. That's why we, in chapter 6, 7, 8, the main focus of chapter 6, 7, and 8 is to find H. That's why you do chapter 6, 7, 8. How do I find H? To put in Newton's law of cooling to get the heat transfer Q. That's the name of the game. If H's, they can vary. I'll just give you some rough numbers. Let's say this is for gases. H goes between 25 to maybe, these are just rough numbers, 250. And by the way, H is in watts per meter squared K. Okay. If it's liquids, H is much, much larger. Typical numbers like that, out to 20,000 compared to gases, high number, roughly 250. So if you want good heat transfer, you want to use a liquid. You want to cool your engine block, you're going to use water, because water takes a lot of heat out, not air. Okay. But on the other side of the radiator, you got air. Ooh, I'm going to pay a penalty because I got a very low H because I got air on the outside of the radiator. Well, yeah, that's why we have fins on the radiator. That's chapter 3. Hang on till chapter 3, we'll talk about that. So that's how we engineers work. If we say, oh, my H is too low, I'll do something about it. I'll put fins on it. If I've got water in here, I'm doing good. Take a lot of heat out with water. Convection heat transfer, fluid and the surface. Is it a flat plate? Is it a cylinder? Okay. Now, that gets us down to the, I'll just put this up here, by the way. This Q is called heat rate. This one's called heat flux. You might want to call this heat transfer. That's okay, but the official name is heat rate. It's in watts. Now we get to the third one. Radiation heat transfer. Okay. Can occur in a vacuum. You don't need air or anything. That's why it's so important for space applications, obviously. Because if you want to cool something up there, you got to dump heat from some kind of a power plant or electronics. You got to dump heat, and you can't dump it by conduction or convection into space. No. So you dump it by radiation into black space. So heat transfer from a hot, what is it again? From a hot surface to a cold temperature surface. Okay. And it can occur in a vacuum. The rate equation Stefan-Boltzmann law. Q double prime sigma T S to the fourth. That constant, sigma, is called the Stefan-Boltzmann constant, 5.67 10 to the minus 8 watts per square meter, K to the fourth. Okay. So you give me a surface temperature. Oh, by the way, I will tell you the heat transfer from that surface, but there's a qualifier. That's the maximum energy the surface can emit. Okay, this is for an ideal emitter. The ideal emitter is called a black body. So that's the maximum energy that a surface can emit. But it's only valid if it's an ideal emitter. Black body means like it appears to our eyes to be black. Some surface is black. The phone over there, whatever it might be. We can get really close to a black body, but normally we deal with non-black bodies. So those are other cases. So for non-black bodies, Q double prime epsilon sigma T surface to the fourth. Epsilon accounts for the surface not being the ideal emitter. Its value can go from 0 to 1. If epsilon is 1, it behaves like a black body. Okay. You can find the values of epsilon in the back of the textbook. Okay, so you can find those values for epsilon, polished aluminum, corroded steel, whatever it might be. It's in the back of the book, okay? So, that's what we have for that. Now we have another one, which is the radiation heat transfer between a small object and the walls of a large enclosure. So, here's a small object in a very large enclosure. The walls of the enclosure are at temperature called T surroundings. The object is at a temperature T sub S. The emissivity is the emissivity of the surface epsilon. And if that's the case, then we have this equation for Q double prime. But that's only valid if it's a small object in a large enclosure. Like, put a dime inside of a basketball. Okay, that qualifies. Dime's a small object, 1,000 degrees Fahrenheit, in a basketball, temperature 60 degrees Fahrenheit. Find out how much heat transfer occurs between those two. There's the equation you use. We're going to prove that in chapter 13. That's the proof. Right now we can't prove it. Just accept it and use it for homework. We'll prove it in chapter 13. Okay, so here's the picture. Epsilon is the object's emissivity, Ts, the surface temperature of the object, T surroundings, the temperatures of the wall in the enclosure. Okay, so we have a couple equations in convection, conduction, and radiation, which we use in chapter 1 for the most basic type homework problems.
I might have missed it. For the other equation, that's if it's in space or if it's surrounded by 0 degrees Kelvin.
No, which one, for instance?
The one that doesn't include T surroundings. Yeah, the middle one.
This one?
Yeah, that equation.
Yeah, no, what about, I'm sorry.
That's if it's surrounded by space.
No, that's strictly the surface. Take a surface. Okay. Don't worry what it's surrounded by, just the surface. Okay. And you want to know how many watts per square meter leave that surface. I don't care where they go. Okay. This one here, now I do care where they go. It goes to the walls of the room or the furnace, whatever it might be. Yeah. This one is just the surface itself. Like if I get rid of this, how much energy leaves that surface? There it is right there. Epsilon, epsilon. Ts, Ts. Put in here, that's how much energy leaves. But the problem is, some energy goes out to the walls, but some comes back. Okay. Minus sign. See what it means there? Okay. Okay. It's a good stopping point so I can add people to class after class here. So we'll see you on Friday. If you came in late and didn't get my handouts, come up in front and pick up the handouts before you leave.